This starts the lectures for Chapter 3, Modeling in the Time Domain. This first lecture will be on state space representation. In control systems, we have two primary approaches for analyzing feedback control systems. The first is what's known as the classical approach. This is the approach that we used in the last chapter. It's based on converting a system's differential equations into a transfer function. The transfer function is single input, single output. So it doesn't really consider the internal structure of the system. In this chapter, we're going to look at a more modern approach, what's known as the state space approach. This is also known as the time domain approach. It's more comprehensive because it can handle multiple inputs and multiple outputs. It uses a matrix-based representation to describe the system dynamics. To overcome the limitations of the classical approach, the transfer function approach, modern control theory introduces what's known as the state space representation. This generally offers a more comprehensive description of the system dynamics. So the big picture is a system of order n is expressed as a set of n first order differential equations. These are what's known as the state equations. So for example, if we have a single second order differential equation that describes a system, we can convert that into two first order differential equations. So the top picture is a representation of the system. So inside the box we have some dynamic system state x of t, and x could be in general a vector. So coming into that system we have an input represented by u of t, and that system acts on the input and produces an output y of t. X of 0 is our initial conditions, and typically we're going to let those be 0. So a state space form is typically represented by two things. One is what's known as the state equation, shown here. So x dot of t, that's a first order equation, equals A is a matrix. It's known as the system matrix. X is our state vector. That describes our system. B is our input matrix, and that's multiplied by our input vector. This also has what's known as an output equation. Y of t is represented by another matrix C, the output matrix, times x, our state vector, plus another matrix D times our input. This is kind of confusing, I know, but once you see it in an example, it'll become pretty clear. So for example, let's fall back on something you've seen from mechanics or dynamics. We have a block of mass m, a spring constant k. We have a friction of the block against the wall. We have the up and down motion of the block is described by a y of t, and we have a force as a function of time acting on the block. So here we can write our governing differential equation using Newton's second law. We have my double dot plus b times y dot plus ky equals f of t. So now we have to make a decision. We want to decide on the state variables. So in this case, let's use position and velocity of the mass. So we'll let our position be x1 and our velocity be x2. So x1 equals y, x2 equals y dot, the velocity. So we can take this system and we can transform it into, so this is a single second order. So it's the highest derivative is a double derivative. So that makes it second order. So we can take a single second order system and convert it into two first order systems. So the first equation describing this is simply you take x1 dot equals y dot. Well, y dot is equal to x2. So here's our first equation. Our second equation is found by taking this equation and moving everything to the other side. So it would be minus by dot, which is x2, minus ky plus f of t, and we divide through by 1 over m. So, take this equation and see if you can convert it into this form. So notice it's described by this system is described by a single second order differential equation or two first order differential equations. So why would you do this? Well, one, if you use MATLAB, this is the form MATLAB likes to use. So that's primarily what we're learning this method is so we can come up with our equation that represents the system and convert it into first order equations so we can simulate it in MATLAB. So having solved our equations, we have x1 dot equals x2 dot equals 1 over m times the following term in the brackets. We can now convert this into standard form. So let's take the first equation. We can write this as x1 dot equals 0 times x1 plus 1 times x2. So that equals the matrix, the horizontal matrix 0, 1 times the vertical matrix x1, x2. We can do exactly the same thing for x2 dot. We can, here's the equation. We can write it in this form here. So if we look back at our initial slide, we showed that the standard form of the state space representation is given by the following form. So here we can identify the matrix A here. We can identify the matrix B. We can identify the matrix C. So here, this is y equals, but remember here, y equals x1 dot. So here's your matrix C and here's your matrix D. All right, so the next slide we're going to look at going from the transfer function. We have a transfer function already. How do we get into the state space representation?